In this video, we will do an example involving independence and complements. So the example says, in a certain US state, 23% of residents were born there, so born in that state. 61% were born in a different state, 4% were born in a US territory, and 12% were born in a different country. What is the probability that two randomly selected people were born in different categories? So for example, one being born in state and one being born from a different country. So they need to be born in different categories. Alrighty, so I'm going to talk about two approaches to this. So approach one is going to be a direct approach. So with the direct approach, so we know we're after the probability that these two people are born in different categories, and there's 4 categories here. So this suggests that we're going to have some cases. For example, we could have the first person being born in state, and the second person being born from another state. We could have another case where the first person is born in state, and the second person is born from a US territory. And we could keep going like this. There are several combinations. Eventually we might get to something like the first person is born from a different country, and maybe the second person is born in state. But there are several cases here that we would have to consider. Many cases. So this looks like it's going to be tedious. Okay, so I'm going to put a sad face. We usually don't like having to do a bunch of cases. A few we can handle, but a bunch, that ends up being a lot of work. So as we've often seen, when a direct approach isn't great or it's tedious or challenging, we try to use the complement. So that is going to be approach 2. So we are going to use the complement here. Okay, so what we're after is the probability that two people are born in different, I'm just going to write different categories. Okay, so using the complement, this would be equal to 1, which is the probability of the whole sample space, minus the probability of the complement. So the complement of the event, well, these two people were born in different categories. So the complement of that would be, well, both were born in the same category. Okay, so this is going to be equal to 1 minus. So if they were both born in the same category, well, there's a few ways that could happen. So what were the categories? We got to figure out the probability that they were both born in state. That is one case. As well as the probability that they were both born in another state. And we're going to have to start to add these values because these are disjoint cases from one another. Plus the probability that both were born, let's see, we also had in a territory, a US territory, and then one final case was both are from another country. So we still have some cases to work out, but it is way less cases than I would have if I did this directly. All right. Okay, so in this scenario, when we are selecting these two people at random, I'm going to say, although we are selecting two people, and when we're selecting these two people, it's implied that we're doing this without replacement. So we're picking the first person and then When we pick the second person, we can't pick the same person again. We got to pick a second different person. So although we are selecting two people without replacement, the sample size here, or which is the state's population, can be assumed to be large. And that being the case, we can say, so knowing the first person's birthplace has a negligible effect on the second person's birthplace. And that's important for us because that means when we think about the event where the first person is born and where the second person is born, we get to assume that these events are independent. So the first person's birthplace and the second person's birthplace. Because normally when you select things without replacement, knowing what the first thing that you picked affects the probabilities for the second thing that you picked. But when the population is huge, even taking one person out of it doesn't drastically affect the ratios of the remaining population. Okay, so that said, let's go back to our computation. So we have 1 minus, so for the probability that both were born in the first, both were born in state, let's think about the first person, and then we'll think about the second person. So for the first person, I believe the problem said the probability that they were born in state was 23%. So writing that as a decimal, it's 0.23. And then because we're assuming they're independent, I get to use the exact same probability for the second person. The probability that they were born in state is 0.23. All right, so if I continue in that way, for the probability that they were both born out of state, I'm going to multiply the same number by itself. So the probability that the problem told me that someone was born out of state, in a different state, was 61%. 61% for the first person, as well as 61% for the second person, because we're going to assume they're independent. And then plus, let's see, the third thing was for both from a US territory, and the problem said that was 4%, or as a decimal, that is 0.04 for each of the two people. And finally, for both born from a different country, that percentage was 12%. So I would put 0.12 in both of these parentheses. Okay, and if we work out what this number is, it ends up being 0.559. And that's our probability. If I wanted to write this as a percentage, this is 55.9%. So there's a little over a 50% chance that these two randomly selected people are going to be born from different places. So finally, in terms of our goals for this section, we've completed our third goal. Over the last two videos, we've talked about how we can evaluate the probability of an intersection, so event A and event B happening, when our events are not independent and when our events are independent.